Yeah, so hi, my name's Daniel. I'm a research scientist at Google, and I'm going to talk about some work I did with you and Bo. We're going to divide the tutorial up into three parts. How much time do I have for the talk?
Uh, Three parts all together, 2 hours.
Okay, so I'll do 30 minutes. Is that okay?
30 yeah, minutes?
I
think we'll do 30 minutes talk, and maybe you give 5 minutes Q&A for each subsection, and maybe we take 5 minutes break between the three sections. And at the end, if there are questions about all the three sections, feel free to jump at the end too.
Cool. Yeah. That okay. Yeah, that sounds great. That's super cool. Yeah. So great to talk about our work. So the work I'm going to talk about is based on this talk is going to be based on this paper, Big SSL, exploring the frontier of large-scale semi-supervised learning for automatic speech recognition. This was a paper written by a large group of people. So my co-lecturers are both also in this paper as well. Let's start with a brief introduction and some motivation. Semi-supervised learning refers to the utilization of unlabeled data for improving a supervised machine learning task. So it's kind of a broad catch-all term. So due to some key advancements in semi-supervised learning for speech recognition, we're at the point of being able to leverage large amounts of data, and as a result, benefit from scaling up the size of ASR models. The former is kind of more important than the latter, because if you can't really leverage large amounts of data to train your model, there's no point in making your ASR models bigger, one can argue. So in our work, we studied the effects of scaling both the dataset size and the model size up, and attempted to explore the frontier of both axes of scaling. Yeah. All right, so let's first kind of get into what we mean by semi-supervised learning. Since this is a tutorial, I'll try to be kind of basic and be kind of pedagogical. So please let me know if I'm going too slow or going too fast. So the goal of semi-supervised learning is to utilize unlabeled data to improve the performance of a task that has labeled data. So semi-supervised learning, or SSL, has been especially instrumental for improving the performance of speech models, since data labeling for speech is difficult or expensive compared to other standard ML tasks. So methods for effectively utilizing unlabeled data can enable one to harness the full potential of large, deep models, because you can, in principle, access practically an infinite amount of data if you're collecting unlabeled data. There are caveats to this. There's obviously better quality unlabeled data than there's higher quality unlabeled data, of course, but in principle, this is a much easier problem than labeling large amounts of speech. Another development that's kind of crucial, that's kind of an important backdrop for this, is the emergence of attention-based models. So we all know that in 2017 we had these transformer models introduced into the literature, and many people actually applied these advancements to ASR models. So there's a list of people that have worked on this. For now, we'll be focusing on the conformer developed by Gulati et al. By the way, if you have any questions or comments, like, please feel free to jump in and ask them. Be happy to engage. Great. So so let's try to kind of divide up semi-supervised learning into kind of like smaller into subcategories. We're principally going to concern ourselves with two different types of semi-supervised learning. One is unsupervised learning, and the other is self-supervised learning. So when we say unsupervised learning, we're referring to a semi-supervised learning method where a loss that is helpful for learning the representation of the unlabeled data is kind of designed and used to train the model. So this is training a single model essentially with unlabeled data, but you define some kind of loss that you think will be helpful to learn, quote unquote, pre-train the model with. And you just feed the model unlabeled data, and the model just learns something by optimizing that loss. So a very successful example of this is kind of the next token prediction task that's used to train language models. And this is this has been a very successful way of training. So there have been a bunch of unsupervised learning methods developed for speech recognition. So I believe Bo and Yu's tutorials will deal with more of them. And there have been a lot of exciting developments in this direction. The specific unsupervised learning methods, but I'm not going to talk about those. For now, we're going to stick to a very successful method that's called Wave2Vec 2.0 by Bevsky et al. So the Wave2Vec 2.0 was introduced to us in 2020, where essentially an unsupervised fill-in-the-blank task for spectrograms are used to pre-train the networks, essentially kind of like BERT, but for spectrograms. But the spectrogram representations are too dense. For example, if we try to guess a pixel of a spectrogram or a single time slice or a single feature in a given time, they're pretty easy to guess from looking at neighboring features. So some kind of compressed vector representation is made out of these spectrograms, and a contrastive loss, and then you're essentially doing kind of fill in the blank, training on a fill in the blank task on this compressed vector representation. But then you're at the same time training some kind of model that's generating that compressed vector representation. So in principle, the model can cheat. For example, you can have a simple model where everything is all the vector representations of all the spectrogram features are just 0, and you have 100% accuracy in predicting filling in the blank of those features, right? So a contrastive loss is used to prevent cheating, that kind of cheating. And so what to me was most the biggest a pro of this method is that you can leverage essentially a very large data set. And even if you have a tiny amount of labeled, a small labeled data set, it can really, by leveraging the knowledge you've acquired from pre-training on a large data set, you can do very well on tiny data sets. As we'll see, we're going to talk about self-supervised methods as opposed to these unsupervised methods. And self-supervised methods tend to, the returns of self-supervised methods tend to diminish as you go to, as the labeled data sets get smaller and smaller. So here's kind of a schematic representation of how we use Wave2Vec 2.0 with conformer architecture. So basic conformer architecture looks like this, where you have some input features. There's a layer that subsamples essentially the input spectrograms. There's some augmentation that you do up front when you're doing standard training. And then there's kind of like these, a linear model here, a linear layer here, some dropouts applied, and the data is passed through a bunch of conformer blocks, and the final context vectors are obtained by some applying a projection block at the end. When you pre-train with Wave2Vec 2.0, what happens is that you generate these encoded features by the convolutional subsampling, and you mask part of the features that are passed into the rest of the network. And then there's some kind of an additional linear layer that you're targeting for that is not masked. And based on this masked information, you're trying to generate guess what the quantized, or what the masked features are, just based on the unmasked features. So it's literally trying to make the work for a dense spectrogram. So yeah. All right, so that's kind of the unsupervised method we'll be relying on. Then there's self-training. In self-training, we machine label the unlabeled data to help improve machine performance. So what we want to do is we want to train some kind of student model with the data labeled by a teacher, but we want the student to perform better than the teacher. So this sounds a little absurd, but actually people have made that work in image recognition. So there's this paper about noisy student training in 2020, where people were able to successfully apply this method by making the student actually be better than the teacher in many different ways. So first, they make the student have larger capacity than the teacher. They make the teacher produce labels from clean input, but then they augment the labeled data when training the student. So when the teacher is looking at the audio and generating the transcripts, it's looking at clean audio. It has a very easy time generating the transcripts, but when the student tries to guess the transcript, you're heavily augmenting the audio, so that the student is learning under harder conditions. And then once you train the student like that, you can set that student to the teacher, and you can kind of iterate. So this is kind of a schematic representation of what noisy student training looks like for speech. So we've done little tweaks to make it work kind of better for speech. So for example, given your data, again, like there are, we have a set of unlabeled data here and labeled data here. And this data set here is like some data set generated at some generation. So in the beginning, you just start with the labeled data. So you first train your student something, well, the semi-supervised learning improves the task itself already. So you might think, hey, say I trained some kind of model on 30,000 hours of data, like, do I need to do, can this be made better? And the answer is yes, by utilizing giant amounts of data and training these giant models, you can still make a 30,000 hour task even better. But the other lesson was that we were able to improve data efficiency by a lot. So we were able to get kind of similar results to existing SOTA on this particular task by using 3% of the data. So semi-supervised learning and scaling up was really impressive in terms of like data efficiency, more so than just performance gain. So the other result, which you could argue is pretty predictable, is still that the scaling up pushes existing benchmarks, large or small, further. So if you look at the second kind of plot, we were able to, by using these scaled up models, just improve state of the art on various existing ASR benchmarks, large or small. So these benchmarks here are all public. They range from whatever, like hundreds, tens of hours to 100 hours, about 1,000 hours of audio. But these tasks are kind of industrial scale tasks that have tens of thousands of hours of quote unquote labeled data. And we were still able to improve that by a non-trivial amount by scaling up. And then the other like kind of surprise was that the representations produced by scaling up improved non-semantic tasks too. So we're all used to word array rate, so we view lower as better, but here the non-ASR by scaling up improved non-semantic tasks too. So higher is better. We're all used to word. These are some accuracy measures on a bunch of non-semantic tasks. For example, speaker identification, or telling if speech is masked or not, sound classification, and so forth. By simply training a simple linear classifier on the representations that can be found inside the giant conformer, we were able to just beat existing like state-of-the-art numbers by just utilizing these representations. So that was like very surprising to us, actually. Yeah, are there any questions about this before I move on to kind of particulars of our results? Okay, cool. Yeah, so those are kind of the punchlines, but there were like various kind of lessons learned in the process. So let me kind of go over them. So these are kind of a subset of lessons that I found interesting. So one thing that was super interesting to us was that these models necessarily, as a model gets bigger, they necessarily have to be pre-trained, which was surprising to us. So here's an example of LibreSpeech that we all know and love. And this is the performance of a model trained on LibreSpeech, but as we make the model size bigger. So here's a 100 million parameter model. These are all conformers, 600 million parameter model, and a billion parameter model. So if you just train on LibreSpeech from scratch, maybe we're not doing a great job at hyperparameter tuning, but actually in our defense, hyperparameter tuning cost as the model gets bigger is very expensive. So, we've tried to make this better by purely doing hyperparameter tuning, but still, the best numbers we were able to get on LibreSpeech by training from scratch actually gets worse as the model gets bigger. But once you pre-train the models, then the models behave normally. So the word error rate, as predicted, as models should, right? Like as the model is bigger, we want the performance to be better, and to make that to make that normal progression happen, we have to pre-train the models, at least to our, maybe there's some magical initialization or training scheme that we don't know about, but at least like this is what we've been able to do. So very interestingly, if you look here, if you go from 600 million to a billion, LibreSpeech training from scratch gets worse, but actually when you have a larger data set, it does get better. So this is kind of the voice search data set with 30,000 hours of data. And you actually see that as the model gets bigger, like it does, like the performance mildly improves as you, so you might view this as really a classical overfitting problem, maybe. I think there's some debate, but This behavior kind of reverses here, but still, when you scale up to 8 billion parameters, actually, it's just very hard to make the model even train or converge in a reasonable way once you get to 8 billion parameters. So it seems like ASR tasks like RNNT or CTC kind of tasks are very, very hard to scale up, whereas the pre-training task seems to be easier. And maybe it's because the pre-training has more data, but we're able to pre-train those giant models successfully and make the performance better. The other thing we found is that, again, like semi-supervised learning is great for efficiency. So if you look here, we have two kind of models. So the first plot is the performance as we make the model data set bigger. And this is a single model. This is the 600 million parameter model. And the green line is just doing unsupervised training, and the blue line is doing unsupervised and self-supervised training. And we see like as the data set size gets smaller, the efficiency increases like vastly. So for like a tiny data set, by employing these SSL methods, we can improve the performance drastically when the labeled data set size is small. And as you see, as the labeled data set size gets bigger, the effects of scaling up become smaller, right? So down here, you're able to, as you make the model bigger, the improvement is like visible. Like this is a log scale graph, so the improvement is pretty significant. But when your data set size gets very, very big, the improvement from scaling up your model kind of diminishes. You have diminishing returns. But this is something you can kind of like predict, but yeah. The other thing we found was that we see lots of cross-lingual benefits, especially at a low data set size. So Bo's going to talk a lot more about multilingual setups, but we find that in the low data set regime, we also see cross-lingual benefits. The other interesting thing we found was that, as I told you, right, like we were able to get very good non-semantic representations of the input audio inside the conformer. What we found was that so this is like the layer in which we find the good. This is the performance, the average accuracy measure of these non-semantic tasks based on the representation in the layer we got the representation from. So this blue line, for example, the conformer XL has like about 23 layers. So, this is like the first layer, and this is kind of the last layer. And we see that like kind of always the layers in the middle kind of do the best. So we want some representation deep inside the conformer model we want to use something deep inside the conformer model to give us kind of good results about the non-semantic content of the audio. So I found that interesting. So yeah, I think I'm right on time. So the advances in semi-supervised learning for speech recognition has opened kind of, we're all living in it now, a new era for ASR, where researchers are kind of now looking beyond just improving kind of public speech benchmarks. We're looking beyond that, I feel, and aspiring to train giant universal speech models that can do, many different things. So I think I'm very excited about this, and we'll talk about more kind of exciting, more recent developments by Bo. Bo and you will be presenting kind of more recent, more exciting results than this. Yeah, so I think that's my talk, and thank you for listening. Are there any questions or? So I can't see or hear anybody, so.
May I ask a question?
Sure.
Hello, I'm Hong Yi. I have a question. You show a very large self-supervised model with 8 billions of parameters. Oh, I know it's already very big, but does Google have the plan to train an even bigger self-supervised speech model? Because as you know, compared with those natural language processing model, usually they have today they can have more than 100 billions of parameter.
That's right.
And I believe speech is more sophisticated than text, right? So we need an even bigger model. So are there any plan to train a bigger model, or are there something that stop us to train an even bigger model?
So I don't know how to answer that in a good way because I've been mostly so I think Bo or you can speak better about that because I actually don't know a good answer for that.
I can
Yeah,
answer that.
sure.
So I think the question is for ASR or for general speech task. I believe for ASR, like at least for now, from what we observe, like 8 billion models, things like already can achieve pretty good performance. So if you look at like a recently larger model trained by other giant group like OpenAI, Whisper is 2 billion, and Facebook published the XLR that is also 2 billion. So I think if you're just focusing on ASR task, let's say like speaker understanding task, classification task, I think I wouldn't say like scaling up the model further, there's no gain, but the gain gonna be like not as big as language model. However, if we talk about like speech generation task, I think for sure like we need a larger model. And like you mentioned, I think from a point of view, like the complication of the signal, like text is part of a speech signal. So I do believe like for those tasks, we need even larger model.
Yeah, thank you very much for your answer. Thank you.
Thanks to you.
And actually for speech, it's more challenging to scale up than text if you simply consider the redundancy information inside speech, and also the like sequence length is a very practical issue. Like you can easily train a text model over 2,000 tokens, but if you map those 2,000 tokens to speech, that's gonna like 10K tokens. And if you further map it back to the scaling law for the model size, it's actually the amount of a compute need for 8B model already similar to the 100B for text model.
Yeah, thank you very much. This is a very good insight. So when we train an 8 billion model, the computation cost probably is already as big as 100 billion model on natural language processing. This is a very good insight. Thank you.
Hello?
Yep.
Yeah, this is Chen Li. Yes.
Hello. Yeah.
Yes. Hi. Thank you for a good tutorial. Now, my question is about some in many application domain, language modeling is actually more important than acoustic models. So I believe some companies, they would rather have their acoustic model not as big, but being able to integrate their own language models into the recognizer. So for what you have right now, it's a so-called general purpose recognition engine. but for many applications, this is not really good enough for specific domains. So in this particular setup, is there a way you can also integrate your own language model into such a setting?
Yeah, so I think that's a very, very good question. Essentially, you can mix and match the particular component we kind of focused on, right? Like today we focused a lot on the encoder, and you can view that as trying to make a very good acoustic representation of audio data. And you can kind of view it as a component of a much bigger system in that way. And there can be various ideas that expand upon that point, which I think like a lot of other people have demonstrated. I think like you and Bo can like as we go on, like this paper was from a year ago, so we're kind of like at like kind of a beginning point of like scaling up these models. But I think you and Bo can like their tutorials can like address like a little bit more of what you're thinking about. But I agree. Like I think this the like in a more modern viewing, by modern I mean like a lot changed over the year. You can view this as generating very good acoustic representations that can be further used by, say, like another big part of a big language model to do other things. So I think that perspective is out there right now, which wasn't clear to me, us at the time. Yeah,
well,
that's a very good point. Yeah,
I think if you push in the direction of large general acoustic models, then of course we are talking about human performance, right? It's human is very good in general purpose speech recognition, but not always. For some topics they are not as familiar with human beings. They have to adapt to the conditions of speakers and speaking environments and so on and so forth. So we will have to deal with adaptation later on for such big models. And I believe that's, some of the applications Bo and Yu will follow up with. But I believe, yes, this kind of adaptation or transfer learning actually is more important in many practical settings.
I think that's a very good point. And I think that's also demonstrated by the large language model research, right? So like all the juice now, like people kind of think pre-training solved, and now like all the juice, all the kind of interesting stuff comes from fine-tuning those language models for specific purposes and coming up with smart ways of utilizing something like that. So I agree with you. I think that's a very I think that's a very insightful comment. Thank you.
And thank you.
Well, I guess if there aren't any more questions, I guess, do we have a break, or are we going to move over to use?
I think maybe let's move to the next one. Sorry, everyone. Cool. I think just to give it a time, like we don't want to drag it too late for the session, so we'll keep to the next one. I mean, if there are like a time, we'll have a break after the second one. Thanks, Daniel. Cool. Thanks to the people asking the question there.
Thank you.
Let me bring up my screen. Do we have my screen? I don't think so, right?
No, I can't see it.
Yeah. Errors. Oh, I have some problem here. Let's see.
I don't know who has the control. Maybe Daniel
yeah.
has to release the control to you.
Yeah, I kind of stopped sharing, so it should be
okay.
fine.
Okay.
Yeah.
Okay.
Because I think I cannot put it. Let me see this one.
Daniel, another way is that you control the slides you present again.
Yeah, if I cannot do that.
Well, okay. So there's a little. Can you send me your slides?
Okay, let me send you the link.
Actually,
yeah. Just send to the chat. Thanks for that.
Oh no, this is my. This is not my.
Yeah, personal one.
Yeah, because yeah.
Okay, let me send from actually from the email.
Oh, actually, I can. Yeah, I think I can get it. Yeah.
Do you have the email there?
Yeah, I'll get it.
Cool, thank you.
Yeah, hopefully.
Let's just. I'll just reply them email again. So it's.
I got it.
Okay,
so
cool.
It's the PDF, right?
The PDF one. Yeah. Thanks.
Yeah, get it. Okay.
Okay, so well done to pull up, have a pulling up the slides. Okay, there it is. Cool, thank you. So I think in previous section, as thanks to Daniel for laying the foundation, like we have been found a large interest in self-supervised learning and gigantic models there. So in this section, we actually try to look at towards another dimension. So basically the multilingual perspective. I think like just now also like properly mentioned about like the large models, how to reach like a human capabilities for that. I think another aspect is like this model on some aspects actually maybe a little bit better. For example, for a human to learn a lot of language is hard, but maybe from our findings, like for a model to capture different language, actually you do not need a lot of a lot of effort, a lot of challenges. That's like this kind of multilingual is looking at. Let's go to the next slide. So basically in this session, we'll look at two problems. One is like scaling up. So how do you make a such gigantic model to capture more language, to handle more language there? And the second part is like how do you further improve the quality of this kind of training stages? Because like normally we do self-supervised learning and then do fine-tuning and additional on that, maybe now it's student iterative learning there. And we'll try to see like can we make it further improvement on top of that. So basically like the joint supervised training approach. Okay, next one. So basically, just here is we put some reference. Basically, the talk of this part of talk is based on this three pieces of work. And next one, and so for the massive multilingual part, just to recap the problem. It's like it's concerned about dealing with a larger number of language, and in terms of massive, it's like the number of language and the amount of data per each language, and it has some pretty good benefits in practice, like training development and both like R&D part for if you do monolingual, that scaling up is challenging, but if you can next the machine learning models to handle all the variations of language, and all you need to care about is just the downstream. How do you like route this model to different traffics there? And also like another perspective is like usually from the literature of the multilingual research, that the data sharing, data pooling across language, especially for low resource and tail language, that's the huge benefit. And if we can benefit using the high resource and learning from the data to encourage the sharing, that will be good in terms of transfer learning and also like a zero-shot capabilities for this large model. So basically, for this task, basically we want to build we look at the end-to-end model. So I mean, it's like most popular topic right now in the field. So basically, we look at to build a single end-to-end model for multiple language, and we want to ensure the quality is like comparable or even better compared to monolingual models. And meanwhile, like we have the benefit of production knowledge and simplicity. And so basically, like from previous Daniel's talk, we see like a pre-training improve efficiency. We still want to further extend to the scale of the language. And next one. So I think just now in Daniel's talk, we also touch upon the capacity. So basically, like the model size, we go up to from 600 million, 1 billion to 8 billion. And then another interesting point is like given the massive multilingual setup, what's the capacity problem? It's like do we need large models to capture that, and how in what kind of scale? So in that sense, we try to understand that based on a particular setup we present here. We look at the 66 language. There is like around 600 million supervised data, and it's around 670,000 hours transcribed data there. And the scale of the language varies quite a lot. In this figure is log scale. So basically the amount of supervised data actually differs quite a lot from the high resource and to the low resource one. So next one. And I think given that data scale, so to understand like this kind of scaling up, we manually split the language into 15 languages, 32 language, and 66. So basically 3 subsets, and some basic stats is over here. And also in previous plots, the color coded like different colors corresponding to different language, and it's like each one is like try to add more language. So we want to see like with this kind of procedure, like how does the model really needs like a large capacity or not. Next one. So basically like about observation, high level observation punchline here is just like a larger model capacity is needed if you want a good quality on more languages. And here we have some detailed results there. So we look at the first figures like on ENUS, how does this kind of scaling up the model size? Actually, the benefit is relatively small on the ENUS side. But if you look at on the B and C and D, so those are multilingual on 15 languages, 32 and 66 language. Definitely, like given a large model size, it improves the quality there. So overall, I mean, there are details in the paper, but here in terms of time, I just like to highlight is like basically we need large models to ensure the quality. So that is like the observation there. So can we do better on that? So basically, like yes, we can definitely push to have huge models, but are we at the best point that everything's well optimized or not? Are there any space we can further improve? So that's what we found in the next slide is like using a different learning schedule for to improve, given a fixed budget to improve quality. Next one. So basically, like we found in one of our studies, like using lifelong learning. So basically, we instead of like training everything from scratch, like if you have 60 languages to train from scratch, or if you have like further 85. Oh, sorry. So the further later study we also did 85, which is not updated to previous, but here we have some numbers there also. So basically, like if you continuously increase the number of language, one better way of like doing that is like you just reuse. Basically, you transfer the learned knowledge from the old model to the new set of language. That is better than you're training everything from scratch. So basically, here we found that the best strategy is that you can start from 15 and to 32 and then 66 and further like even more like 85 also some languages. And from the table, the results, the two red box highlighted one is that basically you can train one model from random initialization, train from scratch. But if you compare to a learning from like a lifelong learning approach, it's definitely like worse compared to the reusing the existing checkpoint, which is like a transfer knowledge learned from previous model to the new setups there with new language, which is definitely much better compared to everything learning from scratch. So that's basically one observation we have found in this space of extending the model to more language coverage with a given fixed model capacity. Next one. Okay, so I think there, as I mentioned, like so far, based on the self-supervised learning, usually there's multi-stage. So basically, you have self-supervised training, and then you have fine-tuning, and probably with noise to a few more iteration. And then from previous study in the multilingual perspectives, like if you want better quality, probably you need to iterate like a lifelong learning approach to gradually scale up. So those, I mean, there are multiple stages that there would be better. Can we simplify that? And from another perspective, actually, it's because like throughout all the fine-tuning part, so one major concern is like the self-supervised learning knowledge maybe just be forgotten, because like it's a huge problem for neural networks, like catastrophic forgetting, because you are fine-tuning on a particular supervised data set. Then the previous self-supervised learn knowledge can just gradually lost throughout the training. So that's why we will look at the joint approach. Can we do joint training to maintain both the self-supervised knowledge and the supervised approach? So next one. And so just here, it's just a recap what Daniel had done. It's like in this particular setup, we look at conformal-based models, and this is just in the literature what the XLSR on the labor speech work, multilingual labor speech has done. Basically, you have feature encoder, you have combinatorial module with the vector module and the contrastive module here, and you have to learn a contrastive loss. And next one. And then during the fine-tuning part, you add stick a decoder on top of the encoder, and then you optimize this kind of joint loss, this cross-entropy loss given the supervised paired data. Next one. And in our study, we found like we want to use the joint trained model with both supervised and unsupervised in a single stage instead of split into two stages. And in terms of unsupervised loss, right now we look at the contrast loss, the wave-to-back loss, and the wave-to-back Birch mask language model loss on the audio perspective. And the supervised loss, basically we explored in our work is like the RNT supervised loss. Next one. So here is like a brief this architecture for the just joint unsupervised and supervised training approach. So basically, you have the feature encoder, which try to compress your feature into like hidden representations, and then you through a quantization module to learn this kind of context vector, and you have the wave-to-back loss, the contrasted loss there in this figure, and the next one. Next one, yeah, and then on top of the contrasted module, there is the based on wave-to-back loss, you have the ML loss. So basically, you tokenize the speech into the code book vectors, and then you try to use the basically borrowed from the language model Birch experience. Like we try to reconstruct the quantize the token there using a max language model loss there. And then on the right side, besides this kind of contrasted loss and ML loss, there is like we stick a decoder, because the fine-tuning usually will have a decoder, and for the decoder we look at the RNT loss there. Sorry for this part, I went through pretty fast because like Daniel has presented the most of the detail of that. But if anyone has questions, feel free to pop up, and happy to explain more. And so back to, here, basically back to Josh. There's like in this kind of objective box, the dashed box. So we look at the three loss there: the unsupervised, the green colored unsupervised, the contrasted loss, ML loss, and the red colored RNT loss. That's the three loss we look at. And usually, like in the wave-to-back or wave-to-Birch or wave-to-back to there is to ensure the code book learned is that diverse enough. It's not collapsed into a single code vector. We have a diversity loss there. It's like on the right bottom right part of the figure. So basically, in the just we look at 4 losses there. It's like you have the contrast loss LC and the ML loss LM, and the diversity loss LD, and the loss of supervised loss, LS. So in our study, we look at we put just the 0.1 for the diversity loss, which is just more of a regularization term there, and that's the combination of the adjusted loss there. Next one. Okay, so for this investigation, we specifically look at, we're not on that large scale, the 60 or 80 language. We're looking at the public data set, which fastly iterate. So we use this modeling or labor speech data set, and it stacks the 8 languages, including English, German, Dutch, Spanish, French, Portuguese, Italian, and Polish. And there are, it's a common standard in the literature. So we just put the stats table here. If the interested people can take a look. I think like one emphasis I want to put here is basically if you look at the durations for the different languages, that's a pretty large gap from English to like the very low results like Polish or Portuguese, which is 100 hours, but for English it's like 44,000 hours of data. So large like diversity in terms of the amount of data. And next one. So this is like from literature. Usually for the monolingual and whatever approach you really want to look at, like how does this compare to the monolinguals? So basically, we want to make sure the monolingual model does not degrade. So this here we just reference the literature. What's the best monolingual model there? And next one. And this is like given the current standards. So if we do pre-train plus fine-tune, and the results we cite here is from the XLSR paper. Basically, like it's the model, the whip-to-back model is pre-trained on the 53 languages of the total MLS instead of just the supervised part, and also including like common voice and Babel, all the kind of combination of the data. And because like for the pre-training part, you do not need the supervised Babel, so that's much easier to get more data there. And then we only fine-tune on the 8 MLS language here. And also just one note is like the fine-tuning is per language, so that in some sense usually is, I mean from experience usually is better than you do fine-tuning using a multilingual setup. And here basically we can see like if we do like a pre-train fine-tune, we can definitely get better over the monolingual systems, especially on the low resource language there. And the next one. And in our setup, it's like basically as we illustrated in the previous figure, like we use the just combine different supervised and self-supervised loss together. And there are a few like training stages schemas that we can explore. Like we have like a 4 loss component as we described before, and then we can explore like do single stage or 2 stage as a training. For there are a few configurations for single stage. We can do just without pre-training, just supervised loss only, or we can do supervised loss with whip-to-back, the original whip-to-back loss, or we do the plus the whip-to-back merge, and also with the supervised loss. And then for the 2-stage training, we can do pre-training, we can do fine-tuning. That's 2-stage. Another alternative is like we are combining unsupervised and supervised loss. We can do just training and then do another round of fine-tuning. That's also possible. So basically, we want to explore all the possible combination of states. What's the best setup there? And next one. Here is like just a notion wise, like so basically we use LS to replace the RT loss as before, and here we combine the previous LC contrast loss and LM the max language model loss to just the LU to simplify it. So basically we put a weight for to combine the two the beta. Basically we weight the unsupervised loss during the just the fine tuning part. And we compare with the previous XLSR approach to see whether it just can bring better improvement or not. Next one. So here is like if we do beta equals 0, basically it's just like a not without unsupervised loss. Basically just training supervised with the whip-to-back merge, and it already shows gain. So the benefit mainly comes like from the compared to XLSR is the whip-to-merge part, because the XLSR is purely whip-to-back instead of using whip-to-back merge. So basically from our setup, the benefit even without joint supervised unsupervised, we have benefit that's just demonstrate the wave-to-back approach does bring additional benefits to the original wave-to-back part, the contrast loss alone. And we can see that overall on the average is like 8% versus the previous 10.6, the XLSR setup. So that's kind of the best in the literature at that time. And next, when we bring in the unsupervised loss, basically once we set the beta to be greater than 0, then we can see the results in the next slide. Here is basically like if we do the pre-training and unsupervised pre-training plus fine-tuning, that's the standard approach. Like, but given the same architecture, basically we have wave-to-back and wave-to-birch loss there, and so we can see that it gives 7.8. And if we do like a pre-training plus just the fine-tuning, that's also 7.8. But if we do just directly from scratch, that actually give us the 7.3 on average. So that means like on this particular startup, we can like start from just the training. Like from when we combine unsupervised and supervised data together, we can, for at least in this particular setup, it's not necessary to keep the unsupervised training at the first stage. We can just train from the just stage, and for the last one, we can first see like if we do just the training first and then do another pure fine tuning, that it can give further improvement, which is the 6.9. That's the best result we get at that time. So that is basically was saying like instead of we would do like a pre-training fine-tuning and we a better improvement is like we do joint training plus fine-tuning that can improve the quality there. So that's the overall findings from this study. And next one. And we want to further understand the benefits. So what we do is we did more like an evaluation study. So basically we compare the baseline with just we can see like across language the ones actually is pretty consistent across language. And also if with without unsupervised loss, that's just the beta equals 0 and versus just, it's like with this kind of joint training, that's definitely better. And also, if you compare to other like a best model in the system in the literature report on this data set, the just setup is like also one's most actually on the low resource side, which like it makes sense because like the just bringing this unsupervised loss, which is like seems the more general as well to the tail languages. Basically, you try to capture more from the speech aspects instead of over-tuned unsupervised data there. Next one. So yeah, this is I think this is just emphasize like basically we can do this kind of just the training plus fine-tuning. That just seems that's better. And if we look at the per language comparison, like it improves most actually both like high resource, low resource. Like in US, there is also some benefit with the just training, and on the low resource, there is larger gains. So it's interesting to see the one data point we found is on the very tail resource, the conjugation polish, the PT and the PL, and different training schemas actually. It's quite different quantize the tokens, and which can cause a large discrepancy during training. And actually, we found like empirically, just from scratch can better facilitate this low resource language and reduce word error. And that's just some findings on this particular site. And the next one.